the interesting thing about this is that, and this is something, Lenny, I know you've been interested in right along, is does the closeness of the friendship matter in terms of how it affects the other person? So for example, are you more influenced by associating with a more recovered alter with whom you're a best friend compared to if you're only a friend, compared to if you're not a friend at all? Okay, so those are the kinds of questions we ultimately want to address with this. Now, right now we have a very, very basic model. In fact, this is only the default model that R-Siena gives you when you originally set up the data object and the effects objects. These effects are put in by default because usually in social networks, out degree and reciprocity are fundamental. One second here. Never mind. I was just getting a phone call. All right. So what we see here, there is one interesting finding here, even though it's a kind of a very basic, just kind of get your feet wet kind of a model. If you'll notice, the reciprocity effect for BF is about 80% bigger than the reciprocity effect for FNet. Both are highly statistically significant. If you look at the ratio of the parameter, which is the number on the left, to the standard error, which is the number on the right, it's close to 4 for reciprocity on friendship, but it's even, the ratio is even bigger than that, like twice as big for best friends. So practically what we can say is that best friends are almost always reciprocated friendships. Friendships are strongly tend to be, but not as strongly. So what does that tell you? Well, it tells you that indeed there is some kind of a difference between somebody you nominate as a close friend and somebody you merely nominate as a friend. When we looked at a model that only had best friend in it, we couldn't know that for sure because the model would probably be picking up some variance in the friendship network from the fact that the best friend network, from the fact that some of it was also in the friend network, right? So by definition, those two networks are kind of correlated. They have to be, right? Because one's nested within the other. But if you create a model where both are included, now reciprocity can have separate effects in the two. And indeed, it turns out to be quite a lot stronger, fairly dramatically stronger, I would say, in the best friend network than it is in the friendship network. So that tells us that we're kind of on the right track here, that there's something different about that network. Now, will that network turn out to be, to have more behavioral significance for people who are in it in terms of social influence and stuff like that? Well, we have to find that out by creating, by building the model up to the point where it has some relevant effects for those questions. Now, when last we talked about this, the idea was to add the two other major so-called endogenous network effects. That is to say, effects that flow from the structure of the network itself, more so than from covariates. That is to say, from properties of individuals or of the link itself. And those would have been transitivity in 3 cycles. I guess we don't have that model yet, but that will be the next step. Remember that we use forward selection in these models because of the importance of good start values. And so we use forward selection using the last model, if it was a fairly decent converging model with significant effects in it. We use that as a starting point for the next model. And we add a few effects at a time because we don't generally have a good idea of what the parameters for those effects should be.
John, could we right now put those other 2 pieces into the model? Ted?
We could.
Ted, do you want to go to your
Why don't we close that text file, because the programs are, the estimation program is going to need to write into it. Now let's go to the run R-Siena model and look at, I think it's, yeah, right. Okay, so lines 178 and 9. It looks to me as though we got to get rid of a 2FR there. No, not there. The name of the effects object. Yeah. That happened when we did a search and replace.
Oh, yeah. You're right. Good call. Should we rename it, or are we going to keep?
Well, you just did it.
Okay.
So, as always, the include effects object is assigned to the effects object that you're changing, and it also uses the effects object that you're changing, although it doesn't have to, as the place to find the effects of interest. And so that's why the function call looks the way it does. Why don't we go ahead and just run that chunk, and that will add both trans-trip and cycle 3, which are the short names for those effects, to the model. And so you see the includes are set to true for both of these in both networks. Now, if we go down to look at effects, yeah, and now we look at the effects, go ahead and just run that chunk. And now you'll notice the transitivity and 3 cycles have been added to both networks. And now if we go down to Siena 07, well, first of all, let's make sure, take a look at the model object. So Siena model create, that would be, I think it was this model 1 model.
Not here.
Yeah, no, keep going down. So that's the data object. The model object is, keep going down. It'll be around 130 or so, 145. There we go. Okay, so let's recreate the RF mod.2FR, but this time use standard inits to F. Because what we're going to do is, instead of using the standard initialization parameters that kind of Siena roughly calculates from the data, so go ahead and run the chunk.
From this model.
Just run the chunk. There you go. So once again, it's going to write the results into the same text file that we had before, and that's what this statement down here below says. So let's go down to the Siena 07 call, run model. There we go. And yeah, we're going to take, so the mod 1 was, first model was mod 1.2fr.1. We're going to call this mod 1.2fr.2. But we're going to use mod 1.2fr.1 as our prevance. Yeah, that's fine the way it is. Yeah, that's good. Whatever you want to do it.
Should I put the model that we previously used as the prevance?
Yeah, exactly right. Exactly right.
Okay, that's why I was copying it, because this one was, I used one from a preview. Right there, but not 2, but 1.
Exactly. Because there is no 2 yet. If you put 2 in there, it would blow up and say, well, there's no 2.
Yeah.
Okay, and now you
create.
Yep. Okay, go ahead and click on it, and it'll run.
Okay.
So that's all there was to that.
My R is out of commission for the next hour.
Yeah. So, la-di-da-di-da, what do we do now? That's one of the great things about R-Siena. I feel like it's a bit of a throwback to the, I want to say the last century, more like the 19th century, where things were kind of slow, and like, the mail went by the Pony Express and stuff like that. So, yeah, just you can't hurry an iterative algorithm, right, Mike?
So John, in a sense, you had done something not 100% comparable, but with the loan network, where you had basically broken it up into actually 3 different kind of chunks of those who were kind of very much willing to share loan resources in the middle, and then not at all.
Yeah, that was the paper that we did like 5-6 years ago, using that our preliminary data. We had data on 5 houses or something like that, and it was pretty threadbare. But we ran some models on that where we used these sort of different amounts of money that you were willing to loan somebody else as an index of trust or something. Basically, I can't remember exactly what we found there, but there was definitely a difference in the predictors of each level of trust.
So for that one, you actually had 5 houses, of which you kind of broke it into 2 houses versus 2 houses, and one you put to the side. So you're really comparing houses. Of course, we have many more houses now, but that was a different strategy.
The strategy, what we were trying to do there was to deal with the fact that the houses were heterogeneous, but they were too small to estimate a model on their own for each one. So a possible strategy that you can use under those circumstances is to group the networks, the houses together, which will give you a more stable estimate, basically a pooled estimate of the dynamics for the houses that are grouped together. Okay, so they're considered like one house in the sense that the dynamics that create the networks you're interested in are hypothesized to be the same. So fundamentally, from a statistical point of view, it's a pooling strategy. It's nice if you have some empirical basis for doing this. It could be anything from house size, well, any characteristic of a house at all. It could be the size, it could be the amount of variability over time in the relationships. It could be other measures that we have about houses, the nature of the neighborhoods, you name it. It could even be region in our big study where we have basically 3 regions, North Carolina, Texas, and Oregon. And these can all form bases for grouping. And what the way we implement the grouping in the network data is we create, so right now we have one big network for each wave with restrictions, okay? The restrictions being that, you can't form a relationship with somebody who's in another house. And that's where those structural zero thingies come in. Remember we talked about that before? That is in a way a maximal pooling strategy. You're basically assuming that all the houses are the same, except, but the data that you use to infer their presumed joint dynamic effect parameters is restricted to come only from within house tie changes, which makes sense because we have no data on between house tie changes, right? That would be completely uninformative for this question. But an intermediate and then the other extreme would be to basically estimate effects for each house and do a meta-analysis of them, which is great, as long as the networks themselves are large enough and, basically have enough of the correct kind of data so that you could estimate a decent model for each one of them. But the houses are too small for that, right? Many of them, what's the average size, like 6 or 7, something like that? And so that's too small. So one possible strategy, and this is something we may try eventually, we just haven't gotten around to it yet, is to try an intermediate pooling strategy where we create a partition of the houses and basically pool the effects within each partition. That's what it boils down to. And the partitions are defined by, as from Siena's point of view, they look like separate networks. So there might be 3 or 4 or something, half a dozen of them, I don't know. And to Siena, these are all separate networks that you're giving it, but they're actually structurally zero, segregated sets of houses that we're using. But they're subsets. Right now, we structurally zero segregate all the houses in one big, quote, network, unquote. And that's our strategy right now. So does that make any sense? It's kind of a lot of words.
Yeah, so John, we have male houses and female houses. Maybe if we put sex into this model, wouldn't that basically be looking at basically two different groupings?
I think that would be a really interesting idea, okay? So basically we could run it with what amounts to two networks, you know, from looking at it from R-Siena's point of view. But it would actually be all the male houses and all the female houses separately. And what that would do is it would allow the parameters to be different in the two types of houses. And if we have reason to believe that those houses, that the effects really are different in male and female houses, and so far there is some reason to believe that, right? Then we would have learned something. Another thing is that the racial effects that we seem to be finding, like for example, for the paper that we're just working on right now, Mike and Lenny, could be explained differentially by the dynamics in male versus female houses. So I think that would be an interesting tack to take too. You see, there's no shortage of possibilities, right?
So John, there was a time when we, about a year ago, published a paper in the Journal of Community Psych, and we had these 42 houses, and we broke them into those that were highly connected, that were not very connected, and some were average connection.
Yeah, it's a descriptive paper, basically.
So there were three different groupings.
Right.
Would that type grouping also be worth putting into a model to see if there are differences depending on those three types of groups?
It might. The thing is that we actually have measures, effects that we can put in, which, well, let me think about that for a second. It could be a way to go, Len, but I would probably start out by trying to incorporate the effects that we, you know, group these houses on into the model, and to see whether we could explain what was going on the basis of the values of those individual level effects. Because remember that to a very large extent, effects like out degree and stuff like that are going to be they have to be house specific, because you only have other people that you can choose within your own house. And indeed, we know that for some houses, the networks are quite inclusive, and for other houses, not so much. But we will capture a lot of that by simply looking at the effects for individuals. You know, in effect, you're kind of saying that because you don't really have a direct measure of effect at the house level, and this kind of a model doesn't directly separate the two, although there's some indirect workarounds that you can make, that a lot of the individual variability will pick up that house level effect and give you a pretty clear idea of what's going on, but leaving you speculating as to whether the effect is really about the individual within the house or the house itself. Well, that's not too bad of a downside at this point in our knowledge, I wouldn't say. But it's certainly a direction, Len, that we could go in, and a strategy that one can use to try to capture the different circumstances under which an effect will have this value or that value. Again, what we're doing now pretty much assumes the effects are completely homogeneous, both over time and over house. We know that's not true. I mean, it's almost certainly not true. But it's a good place to start, and you find out what you can find out using that strategy, and then you get more granular.
So
yeah.
So it sounds like, John, you're suggesting, I mean, we have looked at kind of length of time in Oxford House at wave 1. That would be length of time. We have looked at gender. We have looked at race. So you would say that potentially putting them in one at a time, or putting them all three into the model to sort of do a next run? What's your...
Well, you always want to do it one at a time before you start doing combinations. And remember that when you start doing combinations of, by the way, you can look at combinations either in terms of characterizing a network in some way, like, you know, male house networks versus female house networks can be analyzed as two separate, you know, pooled within themselves networks. But you lose a lot of degrees of freedom when you do that, right? I mean, you know, you necessarily are trading granularity for raw information in some way of saying it. And that's true whenever you go in for subgroup analyses, you know, in this model, just like any other statistical model. So you always want to start out with the most general stuff you can do, and then get more particular with subgroups, bearing in mind that while you may be identifying stronger effects because they're more specific to the subgroup you're looking at, you also will have less evidence for that effect. So what you're hoping is that the effect size will be enough bigger to compensate for the fact that you've got less data going against it.
So John, you also put similarity in as a variable. Is that something that you would say to be playing with?
If it's similarity, then we have to be talking about similarity with respect to what? Of course, that's meaningless for sex. Usually in mixed sex networks, we always find that you know, sex is a big determinant of a friendship in networks up to and including college age adolescents. You know, for adults, the situation's different depending on the network context, really. But in this case, since the houses are sex segregated, it's meaningless to do that. But you certainly could look to see whether racial similarity has an effect, assuming that you have enough people of the same, however you define race, in enough houses to be able to calculate an effect from it. I've looked at age as a determinant of, I think, all of these networks and found nothing. I mean, it doesn't really seem to be related strongly at all to friendship choices. And I've also looked at recovery factor, because, you know, you might argue that people who are similar in their recovery factors have a tendency to affiliate with each other. So the less well-off affiliate with other less well-off people, and the more well-off with other more well-off individuals. Well, that's not true either. There's no tendency one way or the other for recovery factor to affect friendship choice, nor is there an effect of time in house on, so similarity in terms of time in house doesn't matter. People who are short timers are no more likely to pick each other than people of different lengths of stay as friends or good friends. Well, as friends, I don't know about good friends yet. So, but we could certainly look at that. You know, we could, it might turn out that for best friends, this would be different. And that's probably where I would start. I'd take this model here and I'd run some similarity effects on recovery factor, time in residence at baseline, and age. And I would see if there were similarity effects associated with friendship formation in the best friend network.
So Ted's particularly interested in psychiatric comorbidity, so that could be something that could be thrown in too, to sort of... see if that's relevant, maybe at a later point.
Do you have enough people with severe, or well, what you would consider to be sufficiently severe mental illness to be able to make some inferences about that?
We're going to use the method that we're using now, R-Siena, and across all 7 waves, I have enough people that have endorsed things on the psychiatric severity index to be able to. I do have that.
Ted, you got some feedback coming from your microphone, just to let you know.
I reset my headphones.
So yeah, that again, something I'm just kind of wondering, John, if it might be good just for us to once again maybe go back to you know, just the analysis that you know, Ted has run, so we could sort of see, for example, you know, just look at convergence to show kind of what a convergence looks like, and we could go to some other things. So Ted, do you want to pull up your results once again for your text? If you can't, I can do it myself. I've got the same. Can you hear us okay, Ted? Okay.
Let me see if I can do it with the thing that's running still. I can't open anything because it's still running. Yeah.
Yeah. And because I'm recording, I can't. Let me. Yeah, my model's still running too, so I've got the same problem you do. So that's okay. Why don't we just at this point throw things open to the group? If anybody, or John too, if you know, just to kind of make sure the convergent model did come out like 0.20 or something like that. So that sounded better. So
when we were just looking at, yes, it was the convergence on that was okay. You'd like to have it a little better than that, but for a preliminary model with very few effects in it, that's fine, you know.
And if it doesn't converge, kind of if it's like at 2 or 3, which we were getting initially,
right?
What does one do at that point?
Well, one thing you want to do probably is to eliminate any statistically non-significant effects, unless you have some substantive reason for keeping them in which case you might want to rethink that. The issues here are the same as they are for model building with any statistical approach. I mean, there's no real difference.
So okay, we've got the, why don't we take a quick look at this? So there you see the convergent ratio of 0.22. So you're saying that that is acceptable, basically.
Yeah, the rule of thumb is 0.25 according to the R-Siena manual. You know, again, for a final model, you'd like to have it closer to 0.10 or something like that.
And just for everyone, John, tell us again what convergence means.
Convergence is basically just a measure of the extent to which the estimation algorithm is making small repeated steps around some optimal value of the parameter vector. Okay, so the parameter vector lives in, you know, basically a space of k plus 1 dimensions, where k is the number of effects and the extra dimension is the objective function, you know, whatever it is that the parameters are predicting. So you can imagine if it were just 2 effects, then you would have like you know, what amounts to a surface. You can imagine a balloon, kind of, you know, and the algorithm sneaks along till it gets to the very top of the balloon. And the pointier the top of the balloon, that is to say, the less flat it is, the more easily the algorithm is able to zero in on a particular, hopefully unique point where the parameter vector has its optimal value, however you define optimal. R-Siena has ways of doing that, but we don't have to get into that right now. And so that's really what the convergence is basically measuring how small and consistent the steps are, essentially, that it's making at the very end when it finally satisfies its whatever its stopping criteria are.
Great. Okay.
So John, are those in the list over there, the 21 numbers that first column says averages, are those the actual, those are the point estimates at this point when it's converged?
You're looking at the convergence statistics?
Yeah.
Oh, I have to look at that myself. Hold on one second.
With these headphones, do I still get feedback, or is it a lot better?
Yeah, there's still some feedback you're getting, Ted. Yeah.
Huh. Okay.
Okay. Let me just take a look at, if you want to share your screen, Mike, so I can see what you're looking at.
So
well, I was looking at Ted's screen.
So John, do you see Ted?
Oh, wait a minute. Okay, I'm sorry, I didn't have that screen up.
Ted's screen is up. That has it all in there right now.
There it is. Okay, right.
Fantastic. Good.
So 1 through 21, there's the first column of numbers. It says they're averages. Are those the point estimates that are going to show up in the third section output down there where it says estimates and standard errors?
Tell you the truth, I'm not sure. I once knew what all of those numbers meant, but I kind of forgot. It's in the manual, and so if you want to, read what they exactly mean, the third column is the most consequential, aside from the obvious value of understanding exactly what they mean. But it's essentially a T ratio that indicates how big the jumps are that it's making at the very end. And it's making really big jumps, that T ratio is going to be big, right? And if it's like a kind of a some kind of a moving average of those jumps, if I'm remembering that right. But the bottom line is that if it's zeroing in, with very teeny jumps at the end, that T ratio is going to be very small. But if it's still making very big jumps at the end and it's not sure exactly where it should be, then the T ratio will be big, and that's not good. So it's basically, the last column is the most important, and it gives you an idea of how well the algorithm is doing in pinning down that parameter. But the average is not the parameter. The average is something else, and I can't remember what it is. I'm sorry.
Okay, so that's helpful. Why don't we just go down a little further, Ted? Just bring it down to the, there you go, just a little further down. So yes, that's it, great. So could we just real quickly maybe talk our way through some of these, again, just effects, so that everybody is clear what they possibly mean. We certainly have talked about out degree density, reciprocity. You started with that. The ratios before that, could you just explain what those mean in terms of like 1 through 5, and then for the friend neck 6 and 7, and then we can just replicate that. Just so.
Okay. Well, rate parameters are essentially just parameters that tell the model how many changes it should make between waves, is basically what it comes down to. I believe the metric is logarithmic, basically. It's like, log odds of a change kind of a thing. So if you want to know what the actual log odds of a raw change are, you'd have to exponentiate that. So, you know, whatever e to the fourth is. And these are, remember, they are estimates of latent changes. So we observe certain changes, let's say for, you know, that occur from wave 1 to wave 2, which would be like what the rate 1 parameter is measuring. That's how many changes you expect to have. But remember, in a stochastic model, there can be situations where you see a tie as being the same, both 0, both 1, at both ends, but there was actually some latent change in between and they ended up being the same. And the model would allow that to happen. So there will always be more latent change estimated by the model than there is empirical change. So that's one good thing to know. So it's not simply the number of changes that occurred in the FNet 0 SD relationship between wave 1 and wave 2 that the rate is based on. It's more than that because of the stochastic nature of the estimation, of the model, excuse me. So, but basically it's just an estimate of, you know, what is the likelihood if a person has an opportunity to make a change in his or her network in the simulation, what are the odds that he or she will actually make that change?
John, when you say a change, I take it we're talking about in friendship, just friendship, combining those two categories of best friend and friend. I mean, that's
I mean, the rates are separate for each type of network. So, you know, what are the odds that somebody will make a change in their, you know, friend or close friend network? That's handled by the rate parameters for the FNet 0 SD rates. And then the same thing is true for best friend or close friend, I mean, for the rate parameters 8 through whatever it is, 12 there, I guess.
So just looking at 1 through 5, it looks like those are all significant values. If standard errors are being basically going into the other coefficient, basically, if they're all significant, is that a good thing? Does that mean there's changes going on between each of the waves, or is that a bad thing?
It's a good thing. You know, in general, if there's no statistically significant change, what that's really telling you is that the amount of change can't be reliably distinguished from no change at all. Well, if there's no change, then, you know, since changes are the raw data that you're trying to explain here, I mean, in a way, that's the variability in your outcome variable, okay? And if there isn't any variability, then your chances of explaining that variability are concomitantly pretty small. Agreed?
Yeah, makes sense.
So you always want to have significant rate parameters. And if you don't have it, then that might cause you to want to think a little bit and scratch your head and go, well, maybe this isn't exactly the way I want to try to model this.
So John, when it's
is there any advantage to, because they, relative to their standard errors, they look like they could all be about the same. Is there any advantage to fitting a constant change model?
You could fix the parameters.
You can't force them all to be the same value? You
can. Yeah, you can.
Because that would give you one parameter instead of 5.
Well, what it would do, you know, yes, it would save you some degrees of freedom, and it would also save you some, a lot of estimation time. But you'd probably end up with a model that doesn't fit quite as well. Well, I've done that before. I mean, there are situations that I've found where the, for one reason and another, the rates can be narrowed down to a particular range, but for some reason the estimation algorithm has a hard time zeroing in on them with the kind of precision that it wants to have. But if I'm willing to assume that the rate is about here, you know, which is kind of the value that, you know, the estimation algorithm usually seems to be circling around when it stops, then I can just fix that parameter. And that is something that you can do using include effects, I might add. No, actually, I think you have to say set effect. You have to use a set effect function. I don't think include effects lets you fix them. And then the model will just accept those values. It will fix them. It will not change them during the course of the estimation run. And all of the fit statistics will be based on those values that you gave it. Obviously, you're not going to get any statistical significance stats on those effects because they're fixed. But yeah, so there can be advantages. You know, you can kind of simplify the algorithm a little bit for the R-Siena 07 call. And I used that strategy before, as I said, and it actually can work quite well. But it's mainly one of allowing the algorithm to focus on trying to estimate parameters that you really care about, rather than doodling around with these ones here, which may not be quite as well defined as you'd like by the data. But that's not what you really care about. You know, I mean, rate parameters are rarely of substantive interest. By the way, there's one big exception to that, and that is if you're running a so-called diffusion model. And a diffusion model is one where you have a dependent variable, behavior variable that can only go up. It can never go down. So it's like a, say like an onset variable, you know, onset to, well, in some of our adolescent studies, we would have onset to first drink or first binge drinking occasion or something like that. And we'd be following these kids for 3 years, and sure enough, a lot of them would report such an event. And so basically what we would have is we would have a network model which had what amounts to a Cox regression built into it, because that's how you specify that model for the behavior part. Well, there it turns out that the dependent variable is basically a covariate on the rate function. But you can read about that. There's an article that Charlotte Greenan wrote about that some years ago, and we used that technique in a paper that we wrote back in 2012 or 2013. There's a little bit about it in the manual. So that's a digression anyway. I don't think we're really going to need to worry about that much in this study.
So John, when you kind of talk about 1 through 5, in terms of these changes in the friend network,
right?
When you say the changes, are those changes in density, reciprocity? I mean, what exactly are the changes that you're looking at?
Nope, it's just the gross number of changes in relationships. So a tie is added, a tie is dropped, or the tie remains the same, right? So and it's just how many of them. But the other parameters like out degree and reciprocity make reference to what direction the change is in. So for example, if say if reciprocity is a positive and significant value, then that means that there is a tendency, I think I mentioned this last time, that would mean that there is a tendency where if the last time I had there's a tendency for asymmetrical friendship ties where I choose you, but you don't choose me back, to change either to change to symmetrical ones. And that means that either I drop my tie to you and you don't add one to me, or else I maintain my tie to you, but you add one back to me. So the tendency is for a 1 to 0 tie to become a 1 to 1 tie or a 0 to 0 tie, if you will, a non-tie. That make sense?
Sure. So if everybody becomes kind of not friends of each other, you'd actually have high reciprocity, and yet you would say, you would say that's an interesting way of thinking about reciprocity.
Well, yeah, I mean, you really have, that's one of the reasons why you have to be careful when you're interpreting these things. I mean, generally speaking, a reciprocity effect will mean that, I mean, it means two things. One is it means there's a tendency for friendships to be reciprocated, but it also means that there's a tendency for non-reciprocated friendships to be dropped altogether by both parties. So both of those things are true. They're symmetrical statements amounting to the same thing. But you can actually go and do calculations on the data to see, for example, you know, given where the network starts out, right? Because remember that with a dynamic model, where a friendship and where a system ends up is a function of two things. One of them is the dynamics that predict how it goes from here to there. And the other one is the boundary condition, that is to say, the starting values. Well, the starting values in this case are the data at wave one. If you start out with a network that has no friendships in it, right? How can that, you know, it's pretty unlikely that that network is going to evolve into a network that's full of relationships, but it's possible. It depends on the mechanism, but it would have to be mechanisms that had nothing to do whatsoever with the network structure itself. So it would have to be something like, and then the other problem is how would you obtain evidence about that? So generally speaking, when you have those kinds of degenerate boundary conditions, the model can't do much.
So John, sometimes in a recovery home, you have a group of new people come in all at once. They really don't know each other. They're not friends, but over time, they will become properly friends. So that's a case where you could have very little friendship initially if you have a lot of people coming in at once. So we have that first 14 pretty well down. It's really looking at time. How about basically kind of the ones dealing with the recovery factor, which is 15 through 21. Could you just really give us a sense of how that recovery factor is important to understand?
Well, what you see here is basically the change in the recovery factor. The amount of change is captured by the RF rate. And if you had very, very small values of the parameters, you know, the parameters are, you know, 1.44, 1.166, et cetera. And we go down that first column of numbers of the two on the right there. If those are very small and statistically insignificant, it would tell us there's probably not much going on with that variable in the data, which, as with relationships, would tell us that it's going to be hard to explain change because there isn't enough change to explain. But we see a fair amount of change here. It doesn't really tell us whether it's upward or whether it's downward, but there's enough change there so that there's reason to think there's something explainable, I guess, in that data. It's the same thing exactly as if you have a normal regression model and you have an outcome variable that has very little variance. That's never going to be a very promising target for modeling because there's just not enough information in the data to produce an interesting model. There are no, in this particular model, there are no substantively interesting parameters. The linear and quadratic shape parameters merely have to do with how the change in recovery factor is shaped relative to its own value, okay? So the linear shape parameter is basically saying that there's a tendency for, well, you have to take them together because this is really kind of a polynomial thing here. And it's telling you that the recovery factor probably has a shape like a parachute, okay? It's convex, basically. what that means is that for any given value of covariates, there will be a point that's kind of preferred by everybody, an average point that the recovery function tends to coalesce to. And that if somebody with a particular combination of predictors that we don't have in here, but let's assume there are some, okay, is on this side of it, then they'll have a tendency to slide up to the top here, all other things considered. Whereas if they're on this side, they'll have a tendency to slide up this way. And this is in contrast to a situation where, for example, if that quadratic shape parameter was positive, then you'd have like a bimodal kind of a shape. You'd have a concave up shape, where individuals tend to be pushed towards the extremes of the recovery factor. But in this particular case, and more typically, we tend to see something like this for an awful lot of behavioral variables, that there's a central tendency, if you will, even if you don't know the person's particular value on predictors, for there to be a preferred kind of intermediate position of the recovery factor, a typical, modal value of the recovery factor might be a better way to put it. But it's the shift in that modal value that you really want to predict. So first of all, you have to control for the overall tendency of that. And it's kind of like a mean, like an intercept a little bit, okay? You have to control for that, that location, and then you figure out what explains variation around it, or to put it another way, shifts this way or the other way. This may not be very edifying.
No, John.
But here you go.
This is, what you're really helping us understand. I mean, Mike has been doing stuff with M+, which is really looking at the recovery factor. And we've seen some comparable results. But what's nice about this is here we have endogenous variables, which is the really strength of R-Siena, that we can put two variables in there, the social network and the recovery factor, and they're endogenous. And
we can see how they affect each other is what it boils down to, which you really can't do with a multi-level model.
And that's what's dynamic about R-Siena. The other thing that a lot of these other procedures don't seem to have, the multi-level modeling and other things like that, is that often it's pairs, dyads, which we're talking about here. But now we're actually able to go into triads. We're actually making it much more interesting by having a threesome, which we can't do in these other procedures. So that's the really tremendous advantages of R-Siena that are available to us.
Right. It's the whole idea of R-Siena is that individuals are making decisions. And so effects are all defined at the level, essentially, of dyads, of somebody, choosing to have relationship X with some other person and or vice versa. Where, characteristics of both the network neighborhood that they find themselves in and of their behavioral profile and of the other person's behavioral profile can all factor into explaining why these choices occur, okay? So it's not necessary that you think of it as a choice model, but that's the reason that it's called a stochastic actor-oriented model. Is because there's this fundamental idea there that it's about actors making choices. And it really makes the most sense when you think about it in that way. This is, in contrast to, let's say, exponential random graph models, which are more about networks evolving in the direction of particular structures. So it can say, well, this network's it's more likely that, you're going to have triangles of some kind forming, but it doesn't really tell you why. It doesn't allow you to address that as a function of, any very direct way as functions of characteristics of the individuals involved or the choices they might want to make.
Right. Well, John, this is although it's very basic, but it's very important to get these understandings. So appreciate this. Let me stop here. We've gone about an hour, and if there's anybody that had a specific question that they have, you know, concerning anything they're working on, let me just give people a chance to throw any question they have at John. But if they don't have anything right now, feel free to come back our next meeting Friday and you know, just bring your work session with you. John is great at helping us debug what we're doing. And this is what's wonderful, because we've got a bunch of people that can just bring things up and we'll bring up these new models, these new kind of elements that we'll put in over the next couple of days so we can kind of see what the changes are. But if there's anybody that, you know, has some last minute question, let me give a little space for that.
John, can you do multivariate wald tests on the covariance matrix of the estimates?
On the covariance matrix.
Well, can you take the point estimates and create contrasts representing hypotheses? Like, for instance, if I wanted to test,
like multiple effect tests.
Yeah, suppose I wanted to test all 5 of those rate parameters are equal.
Yes.
So there's a way to do that.
There is. Just look at in the tests chapter in the R-Siena manual. Okay. And that's exactly what it does. It does a wald test. And it'll calculate it for you.
Oh, okay. So I wouldn't have to do that myself. I would just.
Nope. You could if you wanted, but yeah. Yeah. There's also one thing that we haven't talked about that we will talk about at some point here is goodness of fit tests. And I'll simply mention there that goodness of fit tests, you don't have, since you don't really have a null model in these kinds of in this modeling framework, the goodness of fit tests are all oriented towards how well did the model predict the data, certain canonical aspects of the data, like how well did it fit, you know, out degrees of individuals, in degrees of individuals, you know, how well does it reproduce, in other words, gross characteristics of the network as a whole. The so-called triad census, that's another one. There's any network can be represented by what's called the triad census. And how well is that reproduced by the model? We'll talk about those when we get Nate on board, because he knows more about that stuff than I do.
Great. Okay, so we're going to let people go to lunch now. By the way, if there's anybody who wants to participate in, we're actually revising the paper that deals with kind of racial issues. And we have some issues that John has brought up that Mike has attended to, and we're going to have a quick discussion of that. So if anybody who wants to join us on that, feel free to stay with us. I'm going to shut this thing down so the recording can start recording. John, could you send us an invitation on your Zoom? Maybe you could just tell us what number to use with your Zoom account, and we can use yours just so I can keep mine off, so I won't have to use my same account. Make sure I don't foul up the recording. Do you have a Zoom number, or Mike, do you have a Zoom number that we could use?
Wait, for right now?
Yeah, I mean, so we can.
Yeah, sure. Hang on one second. I just have to remember what it is. It's God, I'm just blanking on it now. Hang on.
This is going to be impressive, John, if you can do this.
Well, I ought to know it. I mean, it's like a phone number, for crying out loud. But I mean, I can barely remember what I had for breakfast anymore.
So Mike, do you have a Zoom number that we could? Do you have a Zoom number?
Oh, here it is. Here it is. Here it is. I found it. It's 362-896-4777. Everybody just call that after we get done here, okay?
362-896-4777. Okay, great. Well, thank you all, and talk to you next time we all gather.
Okay. All right.